Hi, I'm Elizabeth, and today I'm going to be talking about my poetry AI generator, which is my final project for CS221. And first, high level, I want to talk about the motivation for creating this project. So I'm a big lover of poetry, and I think that it would be really cool to have an AI that could generate poetry on the fly. Specifically, the purpose of having this AI is that you can sort of input a seed phrase. So for example, I can say, let us go then you and I, and then have, which is a famous T.S. Eliot line, and then have the AI generate the next few lines of the poem. And so that's sort of the definition of the problem. And yeah, the motivation is just to have the AI produce something that's fun and it can be used as a tool for creatives or just people who enjoy poetry. And now I want to kind of go into what the broad level architecture of my model is. Firstly, I'm going to talk about how I got the data. So essentially, I'm using a Kaggle data set, which is right here. It's a CSV file of 14,000 poems. Obviously, that's too much to train given my computation power, but I'm training on a subset of these poems taken from the Poetry Foundation. And since Kaggle provides a data set, it prevents me from having to do all sorts of extraction work. And now that I have the CSV file, I essentially have to process this data to render it in a format that the neural network can train on. And the way I'm doing that is, firstly, I'm only taking the first 20 poems for now. I'm processing, making sure that we have no NaN values, that we can then take this and tokenize it in a format that is sort of processable by the neural network. And how this essentially works is that we first want to join the poems together. We're placing the /r. We want to produce this corpus of poems that is split. Each poem is sort of split by the new line character. And eventually what that lets us do is fit the TensorFlow tokenizer function on this corpus of poems, which will then allow us to generate a word index, which, as you can see here, eventually will look like a dictionary mapping words to their respective indices in the word index, and they're sorted by the frequency of the word, in the sense that the words that come in the beginning of the index are way more common, such as the and of and a, so on and so forth. Afterwards, we want to convert the word indices, the word index, to numerical embeddings. And what that essentially involves is generating a sequence of n-grams, which means, for example, if we take the line, let us go, then you and I, we generate an array of input sequences of let us go, then so on and so forth. So that allows the model to capture the long-term dependencies rather than just the immediate word before the word we're trying to predict. And we do some more processing here. We're trying to get the length of the longest line, which will be relevant for a model later. We also want to separate the data into inputs and labels. So for instance, like in let us go then, we would take let us go as an input, and then would be the label, which allows us to train our data to predict the next most fitting word. We also want to use a one-hot encoding for our labels to render in a way that the network can better understand. And most importantly, this is our architecture for training the neural network. And this is kind of the bulk of what the model consists of. So I'm going to talk about that briefly as we transition to this doc. So essentially, the architecture of this network is that we first have, if we have a given input, which is, this is not a very poetic line, but that was a great movie, we can essentially, using our pre-processing before, convert this to the relevant index of each word so that we generate a text vector. And then the embedding layer will first start off by embedding each word as a dense vector. And what that will do is it will capture the meaning, it will capture the meaning of each word. So for instance, like similar words might have similar vector embeddings. And then afterwards, we will have a bidirectional LSTM layer, which will do a forward pass and a backward pass in order to use the past to inform the future, but also use the future to inform the past. And that's important because if we're generating a word, we want it to consider what the previous words are, but also maybe what the future words were in the text. And so the way that perhaps we can like concatenate these two vectors in order to take both the past and the future into account. And the reason why we have a dropout is because we want to prevent overfitting. As I was training the model, one of the challenges I noticed was that sometimes the model would repeat the same line over and over again. For example, remember how she, remember, like so on and so forth in sort of a loop, just because it was generating the quite literal sentence taken from the model and then redoing it over and over again. And we also want to have a dense layer, which basically consists of, so the number of neurons in the dense layer is going to map to the total number of words that we have in our word index, and that will let us derive a probability distribution over all of the words, which we can achieve through the softmax activation. And lastly, we want to apply the Atom optimizer, and we want to compile and fit the model and save it so we can use it for later. And last but not least, we're trying to generate our poem based off of our model. So we're going to load our model. Then we enter a seed phrase, which, the user is up to the user, so that user can say anything. For example, if they put, let us go, then you and I, then the model will start generating next most likely words based off of that. And the key thing about this generate poem function, which I'm not going to go too in depth into due to time constraints, is that it essentially works by putting in a sequence, generating the next word, then taking that updated sequence, then generating the next word, then concatenating that word to the sequence and then generating the next. So it's iteratively sort of updating the sequence and then feeding it back into the model. And that's why we're, in this case, we want to use a recurrent neural network structures so that we can take an input and get an output, which then becomes the input for the next output, and so on and so forth. So that way we can get something pretty neat. For example, the last generated poem, which I only trained for maybe 20 or 30 epochs and only on about a data set of 20 poems, was her tender disposition, heart gave out on the dirt, yard little his left him leaning. Doesn't quite make sense, but he screams, I hold him in my lap on the kitchen floor in front of an open freezer. It's not too terrible for being only trained on 20 poems.